Before we move on to the next topic about heap, I would like to recap what we have learned so far in the lecture. We introduced about the idea about priority queue, and then we talk about the implementation of a priority queue using singly linked list. And don't forget, doubly linked list will be an exercise for you to implement priority queue. And we compare the running time for the various operations between either sorted list or unsorted list. And we concluded that for some operation, in the worst case, in either the sorted list or unsorted list, you can get down to linear running time, which is not very good. So that's why we introduced you an alternative data structure called a heap. And we spoke about the intuitive idea about the heap and also its properties, relational versus structural. And also we gave you many examples to really go over. And we talk about how you can do insertion and deletion on a heap. That's what we have covered so far. And now it would be time to think about to go back to the running time for implementing a priority queue. Given that we know about the various operations for the heap, namely how to extract the minimum and also how to do insertion and how to do deletion, the running time. Now we should know what it costs for us to really implement a priority queue using a heap. Let's now do that conclusion, and then we're going to move on to the next topic. That'll be the plan. Right, so let's say we want to implement a priority queue, and what method do we have to support for the priority queue? Of course, you're going to refer to the slides with the interface about the priority queue. Let's focus on 3 of the methods. The first one will be to extract the minimum. Well, in order for us to extract the minimum from the priority queue, what will be the underlying operation for the heap? Let's say we want to use a heap to really implement the priority queue. Well, in that case, we should really just get to the root, because the root is guaranteed to store the entry with the minimum key, meaning the highest priority. And what will be the running time for extracting the root? Well, as we said before, it will just be constant, because just get to the root, return its key or return its entry. And the second method will be to insert a new entry into the priority queue. In that case, well, of course, in the sorted list implementation, we have to insert into the right spot, analogous to the insertion sort, which will take linear time. But using a heap, we will be able to simply just insert and do the up heap bobbling, right? We can insert to the rightmost node at the bottom level and do all the, in the worst case, do the up heap bobbling all the way up to the root. In that case, what will be the running time? As we said before, since the tree is balanced, so the running time will be big of h, which is big of log n. And so this is definitely more superior, more efficient than the sorted list version, which is linear. What about remove the minimum? If we want to remove the minimum, in that case, well, we definitely have to make sure we can also restore the relational property of the heap after the deletion. And we talk about it by doing the so-called down heap bobbling, right? That's something we have to do. And what will be the cost? It will also be proportionate to the height of the heap, which will be big of log n. And if you compare this with the sorted list version, in that case, if you actually want to remove the minimum, of course, you want to find out the minimum first, which will take bigger of n, right? So you can see, again, the heap data structure is really a more efficient way to really implement the priority queue. Just don't get confused. Let me just say it again. Priority queue is the ADT we want to implement at the top, like an interface. And you can think about underneath the priority queue interface, we got several implementing classes. Maybe one will be the sorted linked list. The other one will be unsorted linked list, and the new one we're introducing is the heap implementation for the priority queue. So we got at least three implementing classes for the priority queue. Right, it's a very quick discussion about what we have learned so far. It's always important to know where we are. And the next topic we want to cover for the heap will be how can we actually construct a heap from scratch. And there are 2 cases we want to cover. Case number 1, let's say the list of entries that we actually want to build the heap out of is simply unknown. Simply means we have to supply 1 entry at a time. In that way, how can we build a heap from scratch? That's case number 1. And case number 2 is otherwise. Otherwise means we simply we would know the list of entries in advance to really build a heap from. In that case, is it possible to really go over the entire, let's say, array of entries and build a heap from there, rather than taking 1 element at a time or taking 1 entry at a time, right? So these are the 2 topics we want to cover about a heap, how to do construction. There are 2 cases you want to know how to cover, and always know about the implicit assumption we're making. All right, let's now talk about the first one. Let's see what the problem is. We want to build a heap out of n entries and supply one at a time. So this simply means you cannot simply just write a loop, and the loop is actually going to go over some sequence of entries and build a heap out of there. That's not the way to go. You are simply just given the entry one at a time. When you are given an entry, you want to put it into the heap right away, or you want to grow the corresponding heap right away. That'll be the problem. So for case number one, this will be the implicit assumption. We want to build the heap one entry at a time rather than all at one go, which will be case number two. We'll get there in the next part. And we want to initialize an empty heap. Well, of course, now you can feel free to pause the video and think about how you may actually build such heap from scratch. This one will be more like a warm-up exercise for case number two. I can tell you case number two is actually more sophisticated to deal with. Case number one is rather straightforward. Okay, you can pause the video if you want to think about your own solution. Alrighty, let's now go over the solution together. We definitely want to start with an empty heap. And this will just cost constant amount of time. Just you want to initialize some heap objects, like a tree objects. What about this? And the next step is going to be somehow had to be done multiple times. What we want to do is every time if you supply to me a new entry, let's say E with the K and V, the key and value, you want to insert the entry to the heap that has been constructed so far right away. Right, you cannot really wait until you actually got a list of entries. That's kind of our assumption. You want to grow the heap right away as soon as an entry has arrived. And that's really the part I would like to illustrate a bit together with you. I'll leave some parts as exercises for you, and then we're going to figure out what the running time is. And I can tell you that for case number one, as long as you know about the running time for insertion very well, then you can easily solve it. Let's take a look. This exercise over here is going to be about case number one. Just remember, it's going to be one at a time over here. Right? It will be similar to how we build a binary search tree when we spoke about the tree rotations in the earlier lecture. You can draw some analogy to there. Right? So these are the two principles which I just went over just as a reminder. Let's now try to insert these 15 keys, but I'm only going to insert some of them and the rest will be exercise for you. I will just insert just enough so we can observe the pattern of insertion, and then we can actually figure out the running time from there generally. And let's start with 16, 15, 4, and etc. the order. Initially, the heap will just be empty, meaning that we're going to insert the first key, 16, just become the root. That one is trivial. And for the second key, 15, we're going to introduce a new rightmost node at the next level over here, and then we want to see if it will be necessary for us to restore the heap order property. Let's see. So 15 over here, that'll be the new rightmost node at this level. And then let's see. 15 larger than equal to 16 is actually false, right? Let's make a note over here. So we can see 15 larger than or equal to 16 is definitely not the case. That means we have to swap the nodes. In that case, let me just say swap them. 15 and also 16. This will be the resulting heap. It will be very important for you to note exactly what's going on over here. Right? In this case, the upheap bubbling that we take will be very cheap because the height of the tree is only 1. Right? Just remember that insight, because when I figure out the running time together with you a little bit later, we need this insight. Alright, so that's a heap we got so far. Let me just do a little bit more so you can get used to it. The next one will be 4, in which case we're going to introduce a rightmost node at level 1, and I'm going to put the 4 over here. Right? And let's now check to see whether the heap property is maintained. In that case, 4 larger than or equal to 15 is definitely false. In that case, we have to swap the root and also the new node over here. We're going to swap them. So we're going to swap 15 to be here and the 4 to be here, and this will be the resulting heap we have so far. Right? You can see it's actually not trivial, so you got to be careful exactly what you're doing. So is this the heap? Indeed. 4 is not the minimum out of the 3 nodes. It's definitely a heap. Right? And for the running time for this particular up heap bobbling, it will be similar as before because the height of the tree currently is only 1. So it's pretty efficient. Let's see more. And the next one to insert will be 12 over here. And I'm going to introduce a new rightmost node at a new level. 12 over here. And we're going to check to see over here. 12 larger than or equal to 16. Is that the case? No, indeed, it is not. So we have to swap the nodes. So 16 and also 12. So 12 here and 16 over here. And then we want to check to see whether 12 larger than or equal to 4. 12 larger than or equal to 4 is actually okay. So that's where we should stop for the up heap bobbling. Of course, in general, the worst case would be you may have to go all the way up to the root. So that will be the resulting heap after the insertion. Let's just do one more, okay? And let's say we want to insert the node 6 over here. In that case, I'm going to introduce, and before that, if I may, let me just put this one here, the checking just over here, right? And I'm going to introduce a new rightmost node over here, and that will be 7. Oh, 6, beg your pardon. 6 over here. Right, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Just make sure you keep on track. Right, so 6 over here. Well, is the heap property violated? Indeed, it is. If you compare 6 and 12 over here, so what we have is 6 larger than or equal to 12. Apparently, it is not the case. So we have to do the swap. So swap the 6 and also 12. So this will be 6. This will be 12 over here. And we want to check again. 6 compared with 4. It seems like it is maintained for the heap property. Let me write it down. So now if I say 6 larger than or equal to 4, indeed it is. Right, you can see there are many intermediate details of checks which I still kept in the notes. But you definitely want to make sure you know how they come from. Finally, after inserting the first 1, 2, 3, 4, 5 nodes, what we got this following tree. The root is actually 4, and then we got 6 and also 15 here. We got 16 and 12 over here. Of course, it can keep going until the entire heap is actually built, right? And I'll leave that to you as an exercise. Let me put it there. So it would be your exercise to see what the resulting heap would look like. Complete. Inserting the remaining keys to the heap. Right? And based on what we have seen so far, we should be able to observe some pattern for the running time. Let's now talk about the running time. To derive the running time, we may just want to generalize the scenario of insertions that actually happen when we do the construction for the heap. Let's talk about it. Let me try to draw a general complete binary tree. And not surprisingly, it will just be a triangle like this, okay, in general. And of course, let's think about the nodes that will be at different levels. Let's review the pattern that we learned earlier in the binary tree lecture. So this will be the root, 2 to the power of 0, which is equal to 1, right? That's level 1, level 0. Level 0. And of course, let's say we got 2 nodes over here. So this will be level 1. 2 to the power of 1, which is 2 nodes. Level 1. And let me do one more. Right? I think it's also nice to brush up about the property for complete binary tree. And 2 to the power of 2 is equal to 4. So this will be level 2. Right? It's going to keep growing until we get to the last level. Let's say like that. Okay. This will be 2 to the power of h. So this will be the bottom level, level h. Of course, it doesn't necessarily have to fill out all the nodes as long as it's from left to right. But for simplicity, let me say it's a full binary tree, like a special case. And let's think about, let's say this is the ultimate heap that we have built already in general. What kind of computational work have we done? Let's think about that. the root itself, to really insert it, is like how we inserted 16. That one there is very cheap. That one there is just constant. Let me try to put a running time formula over here, right? Running time. So it will be 1. So this will be the root that we try to construct in the very beginning, just big of 1. And what about at level 1? At level 1 is like a 15 and 4. So these two nodes somehow will actually grow to level 1. So these two nodes somehow, it doesn't really mean ultimately they will be at level 1. I'm just saying that when we first insert them into the tree, they will be at level 1. Because of the bubble, the up-heap bubbling, they might just be promoted up to somewhere along the root. So this will be first inserted to, you know what, let me just write a little bit better. I think this will be important insight. So this one over here, first inserted to level 1. And also, let's say this one here, the next 4 nodes, 12, 16, 7, and 23, I already completed 2 of them, right? It's actually at level 2 when we first insert them, right? There'll be just 1 more nodes I want to make. And of course, you can just keep deriving the pattern. It will be first inserted to level 2. Obviously, you can see 2 nodes and also 4 nodes, and this is what first inserted. They might be promoted up to the root to restore the relational property, the heap order property. Let's now think about the running time for each level. Let's talk about level by level. For level 1 over here, so when the node is first inserted to level 1, what will be the running time in the worst case for us to promote it up to the root? Well, that'll be the worst case, of course, to restore the relational property. It's going to be the heights of the tree, right? That one is going to be simply just 1 over here. Right? So in that way, it's going to be, let me say, plus 2 to the power of 1 multiplied by 1 over here, right? So let me just make some annotation over here. So this part over here is really about, let me use here. So this part over here is about the number of nodes at level 1. And this part over here, the 1 over here, is about the number of levels that we may have to actually perform the up heap bubbling to restore the heap order property. So this will be the number of up heap bubbling step. Right? I think for the first one, I'm going to annotate very completely, but later on, we're going to see the more about the pattern. Right? So that'll be level number 1. What about level number 2? Similarly, but now we just got more nodes over here. Every time we insert a new node to there, what will be the worst case to really do the up heap bubbling? You have to go 2 levels up. Agree? In that case, it's going to be plus 2 to the power of 2. That'll be the number of nodes at level 2, multiplied by 2 over here, which is the heights of the tree. The heights of the nodes up to here, just about here. Sorry, at the depth of the node. Beg your pardon. So at level number 1, all the nodes has the depth just 1. That will be the number of up heap bubbling steps you have to do in the worst case. And when we talk about level number 2, the depth is actually 1 and 2, 1 and 2, and 1 and 2, and etc. And for your own mental exercise, how would it look like when we want to handle level number 3 over here? Well, thinking this way. If we get to level number 3, how many nodes do we have? 2 to the power of 3, which is equal to 8. So, while we could have written even more, would be plus 2 to the power of 3 multiplied by 3. Because, for example, one node over here, in the worst case, you may have to do 1, 2, and 3 steps for the swap, for the up heap bubbling, right? So that's a similar pattern, but let me now ignore that just for now. And how would the pattern continue to the last level? So we're going to say plus dot dot dot, and then plus the last one to do will be at the bottom level over here. And at the bottom level, how many nodes do we have maximum? It should be 2 to the power of h nodes, and for each one of them, what will be the heights? For example, this node over here, if you want to go in the worst case all the way from the leaf to the root for the up heap bubbling, that would be, well, simply corresponding to the height of the tree, which will be h multiplied by h. And since we know the tree is actually a complete binary tree, so h over here is bounded by log n, which I can just put in as log n for now. Alrighty, so this will be log n, right? And how do we simplify this equation over here? Well, this series of sum. Go from here, here, all the way to the bottom level. And let me just box it, and we're going to put this simplification elsewhere on the page. But at least you should see this is how we derive the original sum of the series, series of the sum. And let me just say one more thing over here. You can see this one here is the second term. The second term, all of them, is guaranteed to be less than or equal to log n. Agree? You can think about this part here. It's just about the height of the tree at that particular moment. Of course, the tree's height is going to grow as we get to the bottom level. Initially, the height is only just 1 when we only have built up to here. When we build up to here, the height will be increased by 1. When we go to here, the height will also grow slightly until we actually get to the bottom level when the height has grown to just h or log n. So you can think about the second number here. All of them are really bounded by log n. It's a very important insight to actually note. Let me write it down over here. You can think about the 2 over here. The 2 over here is actually less than or equal to log n, right? Less than or equal to log n. And also for the 1 over here, that's also less than or equal to log n. Right? Let me put a star over here for this formula, for this series of sums. That one should be, the star should be less than or equal to the following. 1 plus this entire rest of the series of sum over here. So let me write it down. It's going to be 1 and then plus, and for this part over here, I'm going to factor out the log n over here because we know every of the second term can be bounded by log n. Right, so I'm going to say plus the log 2n multiplied by, and what will be this part over here is going to be 2 to the power of 1, 2 to the power of 2, all the way to 2 to the power of h. 2 to the power of 1, 2 to the power of 2, all the way to 2 to the power of h. All right, and we are getting very close about the ultimate running time. How do we simplify this part over here? Of course, you can do some geometric sum series if you want to. By applying the formula. But let's take a look at visually what's happening over here. We are basically counting the nodes over here. The nodes over here. Well, more precisely, 2 to the power of 1. The nodes here. 2 to the power of 2. The nodes over here. All the way to 2 to the power of h. The nodes over here. So this part here is exactly n minus 1, right? Because all the nodes together will be n. And now we talk about just without the root. The root has been handled just by this one over here. So this will be equal to 1 plus log 2n. And this part over here will be n minus 1. Right? Just without the root over here. And we can now simplify that further. And this the 1 over here is really the lower term, so we can drop it. So it's really about n minus 1, and the minus 1 can be dropped as well, the lower term. So ultimately, it's going to be big O of n log n. You can see the n is over here and log n over here. Of course, the implicit base is actually 2. That will be the answer. You can see it took quite a bit of derivation over here, but it's also very important for you to see exactly how this running time has been derived. It's very important for you to see that. Right? And maybe there's no need for recap. I think the process has been completely illustrated. You just have to make sure you can also do it independently without my help in the video. Right? You just want to make sure you understand about the abstraction of a general tree that's actually complete and then try to work out exactly the series of sums for the running time, and then you will be able to simplify that. And don't forget, the very important critical step is about this less than or equal to, because we are trying to bound every second term over here just by log n. You should really review about why we can do so.